electricity. Okay. So we're looking at our damped spring. That show up? Yes, it does. So what did we have? We had this guy here like this. This guy here like this. This is our damping term. This is our spring term here. And we set up the equation. We do for F naught. X equals MAX. What do we have? We have this minus KX minus BV equals MAX. Now what do we do to that equation? We write the AX and the V as X dot and X double dot. X dot and X double dot. And then what do we do with the M?
Move it over.
Move it over to the other side. And so that gave us this minus K over M X minus B over M dot equals X equal out like that. What do we know about K over M? We call that the
Omega naught.
that's our omega naught squared, which is our natural frequency of oscillation of the system. So that gives us this right here. And then we assume the form of this right here, BT. And when we did that, that ended up giving us this P equals minus beta plus or minus the square root of beta squared minus omega naught squared, where this beta is by definition this B over 2. And what were the three cases we had? The three cases had to do with the square root. What are they? Yeah.
B equals omega naught.
Okay, so we can have this beta equals omega naught. What was that case called?
Correctly, yes.
That's the critically damped. Okay. What else?
Beta less than omega naught.
Yeah, so we had this beta less than omega naught. What was that one?
Underdamped.
This is underdamped. And the last one that has to be the greater than. What was that one called?
Overdamped.
This is our overdamped. Now, before we kind of get to another topic, I want to show you just this is the beauty of physics. Let's ask, how does this apply? How do these ideas of damped oscillator relate to RLC series circuits? Well, offhand, you could say, they don't. It turns out they do. So let's take a case here. Let's say here's a battery. Just take a regular battery like this. Here's a resistor. Here's an inductor. Here's a capacitor. This is V, this is R, this is L, and this is C. If you're in general physics, 126, and if you're asked to solve this, how would you go about solving this? Am I still clear? I am still clear. What would you do?
Softball.
I basically want you to sum up the equation. What would you do? What do you know about this voltage here, V? This and this are in series. So what do you have to have? You have to have the voltage across the resistor. Now, why am I using a lowercase value here?
Then
Yeah, anytime in electricity, whenever you do circuits, anything with a lowercase symbol is always gonna be something varying with time. They have the voltage across your resistor, plus the voltage across your inductor, plus the voltage across your capacitor. And if there is no battery, V equals 0, and I would just be left with it in here. So, what do you know about the voltage across your resistor for 125? I'm sorry, you don't know anything about it for 126.
I's times bottom.
Yeah, IR. Say no. Voltage across my resistor is a current times resistance plus. And this one might be a longer memory or remember. What do you know about the voltage across an inductor? It's the inductance times the IDT.
Oh, wow.
Okay, prove that to me. Oh, let's get the next one. Now you're going to prove that. Okay, what do you know about the voltage across a capacitor? Plus Q over C. Okay, prove both of these. Proof. Let's start with this one here. That's the easiest one. What is the fundamental definition of capacitance? C is by definition.
Charge.
The charge on the capacitor, okay. Q over the voltage across the voltage across the capacitor. Now in this case here, we don't have capital Q, we have something that's varying time. So in our case, the C here, but remember the C only depends on geometric factors. So your capacitance here is going to be what the charge on across your voltage in it, the charge on your capacitor at any time, divided by the voltage on the capacitor. So your voltage on the capacitor is Q over C. That's where that guy's coming from. Now, how do you prove this guy? Why does an inductor even have a voltage on it or across it? Good review.
So I is EQ, ET.
That's true, but let's figure out what this guy is here.
Change.
What's your quintessential picture of an inductor? Take a tube like this, and you wrap wire around it like this. Now that's an inductor. If I send current through it like this, if I send current through an inductor like that, what does it have? A magnetic field, right? I wrap my fingers like that. That has a magnetic field like this. And that's your magnetic field. Now, if this current is changing with time, what do you know about that magnetic field?
It's also changing.
It's also changing with time, right? Hey, what happens if you have a magnetic field changing with time?
You have an electric field changing.
Connected with what? How do you know that that's true? By
Maxwell
which one of Maxwell's equations?
and
Faraday's law. So what would you have? You have. Am I still clear? I'm still clear. So Faraday's law in integral form is your EMF, which is this guy here, equals minus d phi dt. That's Faraday's law. Okay. This right here, this is like a voltage. It's not right. A voltage is actually given by your integral of net DL. Well, why is it like a voltage and not exactly voltage? How does this electric field differ from the electric field connected to the voltage? Okay, you have conservative electric fields and non-conservative electric fields. What's the distinction? What does it mean to be a conservative force and a non-conservative force? Yep, path dependence. So if we go back to our little picture here, this is I, this is F, if I have this path here, and if I have this path here. If here's some electric field like this, here's some electric field. And let's say this is path 1, this is path 2. If here's my DL like this, and if here's my force, and I'm moving a charge Q, remember the force is going to be Q times Z. So if I want that work, done by that field, what is it going to be? It's going to be that force divided into DL. This is from some initial to final spot. Well, path 1. And this is your Q times D integral of DL. IF like that. Right? Now, if this is conservative, what do you know then about the long path 2?
Same.
It has to be the same. So if this is conservative, this has to be the same thing along path 2 with this guy here. Remember what we did? We worked out last time that if you were to do this, you'd get that this guy here. This would equal 0. And this would just give you this right here. This would be for conservative E field. And this is really what you mean by a voltage. This is the classical definition of voltage. What's happening over here? Is this always equals 0? Not. Right? It equals this mess here. So what does it mean about this electric field? That electric field is it has to be non-conservative. This is a non-conservative E field. This quantity still looks like a voltage, but it's not because it's not conservative. So the name we give it is EMF electromotive force. So the expression looks just like a voltage. Okay, but it's actually, this right here is actually a non-conservative. Okay. So why are we getting a voltage difference here? This voltage difference, in other words, this EMF is being caused by the fact that this magnetic field is changing with time. So we define something called the self-inductance. And how do we define the self-inductance? We take the total flux divided by the current going through through the circuit. In this case here, this is just goes to this phi times I. This L here is independent of the phi. I only depends on geometric factors, and so if I solve for this phi, I get L phi. If I take this and put it into here, what that tells me is that this right here, which is really my voltage on the inductor, is going to be this minus d L phi dt. This is independent of this of the I. This is actually just it depends on the geometric factors. I can pull that out. That gives me this. And what is this minus sign here? What is that minus sign called? That's Lenz's law. And all it means is that the current is set up in such a way to oppose the change in flux. It is a fake minus sign. That does not have to be there. That's why we just have the voltage on the inductor at L dt. That make sense? Good review of Physics 126. And just another reminder, how important that physics 126 is. You take that class. Think it's just for little freshmen and stuff like this. No, you do really profound things in the class. Okay, so let's go back to our little picture. So we have this right here. We have our little circuit. RLC, and we have this one here, which is our V. I'm just writing what we had before. We just stated this is I plus L the IDT plus Q over C. Okay, do I know anything about I?
EQBT.
I is dQdt. Right, so I is by definition dQdt. So what do we have? This gives me R dQdt, for this one here, plus, let's start off here. I'll say no, plus, I'll say Q over C. Start off with this one, then over this one, plus R dIdt. And then this one here, plus L here. Right? And compare it to a damp spring.
Shouldn't those all be
Only if you want it to be correct. Okay. Thank you. Keep me honest. Okay. So what do we have with a damp spring? We have this. That's what we have for a damp spring. So the spring is acting like a what? Well, this is over this over M. I had an over M here. I anticipated something. Sorry. Should just do that. So what's acting like the spring?
the charge?
Which term?
The Q over C.
Yeah, this right here is acting like my spring. So what happens? Your K really goes to basically your 1 over C. Right? Because you can see that your X is going to be the same thing as Q. Consider is my. What's your damping term in this?
R.
My resistor. So my B goes to R. And then my mass goes to what? L. Right, not your here L. So if I just had a simple harmonic motion, if I had simple harmonic motion, purely simple harmonic motion, I'd have to get rid of what term in this case? When does this become purely simple harmonic motion? When there is no
Okay.
there's no damping term. So it has to happen here to have to get rid of the resistor. So if I had this, so if R was a 0, what would we have? We have this picture here. We'll just have this. My equation will become this. And this is analogous to some form of function. What is the charge going to do here? What does the electric charge do in the circuit here? How do you go about solving this? How do you classify this crazy differential equation?
Second word.
Second order,
Homogeneous.
homogeneous,
Linear.
linear. Hey, we didn't know about all the coefficients in front. They're constant. Hey, do we have any way of solving these crazy equations? We're going to assume Q is
E to the PT.
e to the PT. So you assume Q is e to the PT. So that gets, if I do that, I get 0 equals 1 over c e to the PT plus 2 derivatives here. This is L p squared e to the PT. That. They go out. This gives me p squared equals minus 1 over LC. So you know p equals what? My p is
Positive or negative? I. It's the square root of the rest.
see, and I'm going to define this. This 1 over the square root of LC is by definition omega naught, the natural frequency of oscillation. The church. So what happened here, your Q, I could write as some C1 e to the positive I omega naught t plus C2 e to the minus I omega naught t, or how else could I write that?
Sine.
Sine and cosine. So I can also say Q is going to be some C3 sine omega naught t plus C4 cosine omega naught t, or Q is
Some constant.
some amplitude here A,
Sine. Omega.
sine or cosine,
Yeah.
omega naught t plus or minus
Shapes.
some phase angle phi. Okay, pretty slow. Now, before the advent of computers, when things were so analog, what was one way of solving differential equations? And this is true. You could set up a circuit. You could set up the circuit depending on the values you had here, and then you can actually look at what you're getting on an oscilloscope. And that was actually one way of solving these things, and people did that. So when you don't have a computer, you have to be smart. You have to do something clever. That makes sense. So what would happen here? Basically, in a case like that, if you have a charge on, let's say this is t equals 0, what's going to happen? That charge is going to go back through like this and make this positive here like this. But since you're changing the voltage through here, right? Because the current's changing through, you're going to change the voltage. That'll then create then a back current, making this thing go this way. So then the current goes back here, and this becomes positive. This becomes the node. Again, changing in the voltage here, and all this is going to do is oscillate back and forth like that. And that's just an oscillating circuit. That's all that'll do. If you put a resistor in there, then what's happening? Then you're losing part of the energy then to the resistance of the resistor. And then that damping term going down like that is going to go slower, 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 and eventually you'll have no charge to it. That makes sense? Pretty slick. Now, what do we want to start doing? We want to start having actually a driving term on this. So let's ask what happens when we start driving an oscillator. So let's talk about driven harmonic oscillations. Harmonic oscillations. So we're going to do, we now include a driving. So if we draw our little mechanical picture here, here's our spring. Here's our mass, here's our little dash top. This. Now I'm going to have a big flywheel over here. This flywheel is going to move at some frequency omega, not omega naught, but omega. I'm going to have a pole like this connected here like this. So as this goes around like this is going to actually push and pull this like this. Okay? So now if I were to do this, if I were to do my net force in the x direction, what would I have? I have my force in the spring. I have my frictional force just like before. I have this guy here, my driving force. Then I'd have my M and X like that. Now, how do you think I can write that driving force? This is going on like that, so this is flowing like this. That driving force is going to be some amplitude, either a sine or a cosine. There could be some phasing on my omega. I'm just going to say omega t. That. Yeah, there might be some phasing on there, but that just complicates it. So that's our new differential equation. Well, it's not quite a differential equation yet. Let's put it into our user-friendly form. So, what do we have?
Yes.
Minus kx plus, I'm sorry, minus b dx dt. This is f naught. Here, I'm going to put it in the sign for no reason. It's m like this here. Okay, so I'll classify that differential equation. What's the order?
Second.
Second order. Linear or nonlinear? Linear. Now it's non-homogeneous, because this right here, this is the non-homogeneous term. Okay, so what do you have to do with those? Let's see how much you remember from differential equation. What happens when you now have non-homogeneous differential equation? Whenever you have a non-homogeneous differential equation,
Software. Homogeneous.
you must add the homogeneous solution to the solution for the non-homogeneous equation for the most general solution. Okay. So I'm going to give these names. These are not necessarily the standard names, but I'm going to use these names because I think in my mind they're actually the most obvious. So what I'm going to do is, so I will call each of these solutions. YH, and that's going to be for the homogeneous solution. YNH, that'll be the non that'll be the solution to the non-homogeneous equation. And then Y most general for the most general solution. So what this is claiming, so the claim is that Y most general is going to be for your YH plus Y non-homogeneous. Okay. I'll put this in here where YH solves. Okay, so I'm gonna put this. So okay, what did we say this fancy L was? We had this before. When we sort of differentiate equations. I can let this be some AN D X like this, plus AN minus 1, AN minus 1, XN minus 1, A1, D by dx, plus A0. That's going to be some linear differential operator. The linear, a general linear differential operator. So what I have here is that that's my homogeneous solution. Okay. That's my homogeneous solution. The original equation is this. The homogeneous equation is this L acting on Y equals some f of x. This is my non-homogeneous figure. So what is this Y and H supposed to solve? Am I still clear? Yes, I am. So what does this guy here satisfy? That equation right here. And the claim is the most general solution is actually a linear combination of these two here. Now, can you prove that? The claim is that this is the most general solution to the differential equation. Now, how do you prove that?
Let L act on
On that, exactly. Let L. So I'm getting L Y most general equals L acting on YH. It's L making this. This piece here is
0.
0. And what does that equal? F of x. So this tells you that Y most general equals F of x. Right. That's my most general solution. Questions to that? Makes sense? Now, we're going to take a special case. It's going to be the exact same special case that we took in optics. So let's take the special case. Where f of x is simple. Enough with this moves. What did we define simple to be in optics? And also, no, actually, we didn't do this in modern, so it's in optics. So simple means f of x equals a constant. That's like it's simple.
Sine, cosine.
Sine or cosine.
Log, no. Explanation.
Exponentials. Give me all the hard ones here.
Linear combination.
Oh, another polynomial. Another polynomials. Now, you could do linear combinations or products of these. But linear combinations could also do this. I'm just gonna say products of these. Okay. So in other words, as an example here, I could say f of x be something like x squared e to the minus 4x. I'm taking a polynomial times exponential. Perfectly fair. You can even put a 5. I can put a sign in front of here as well. That's okay. Often we do that, but it would be simple. So remember the technique we're going to use? Method of.
Yes.
Oh, we already guessed. Okay. The method of undetermined coefficients. Okay, so I want to set this up again. How you do this? You're going to see the same thing again in objects. So you're going to see the repeat episode. We're going to go over that. Then we'll do some examples, and then once we get that spring down, I want to say something about Fourier series, a little bit about Fourier transforms, and then we're going to switch gears entirely once we get that done, and that'll mark the end of the material for the first step. Our first test is going to be next Thursday, not this coming Thursday, but next Thursday. I think that's even true. And after that, what we're going to start doing is actually we're going to start looking at one of the big topics in your education. That's going to be Lagrangians. Lagrangians will then go naturally to Hamiltonians. That's when you become a grown-up physicist when you start to look at Lagrangians. Okay, every day.
Yeah. Can you remind me what ansatz means?
Ansatz is basic. Okay, I'm going to tell you how I interpret